Alrighty, so today we're going to continue talking about rational functions. We finished off yesterday talking about in behavior, what's going on here? In behavior asymptotes and x-intercepts, y-intercepts, and sign changes, things like that. Okay, and I put a star next to these in behavior asymptotes. I'm going to shorthand in behavior asymptote to EBA. Vertical asymptote will be VA. Horizontal asymptote will be HA. Just because I'm lazy and trying to say what? EBA. In behavior asymptote. This will be VA, as in Victor. But yeah, so that's what's up there. Recall, when you're dealing with a rational function, if the numerator's degree is less than the denominator, automatically goes to y equals 0. That is a horizontal line, therefore that is a horizontal asymptote. If the degree of the numerator is equal to the degree of the denominator, then you divide the leading coefficient over the leading coefficient, which, by the way, will be a number again. So once again, a horizontal asymptote. However, if the degree of the numerator is larger than the degree of the denominator, we're dealing with some kind of other in behavior asymptote. It could be slanted, meaning a linear equation with a slope and a y-intercept, or it could be a quadratic or a cubic or so on and so forth. Okay? Okay. Vertical asymptotes are anywhere you tried to divide by 0 that doesn't cancel out. Vertical asymptote. If you would like to know where your graph crosses the x-axis, just think about the fact that on the x-axis, y equals 0. But if your function is y equals a fraction, how is it possible that the fraction equals 0? The only way it's possible for a fraction to equal 0 is if the top equals 0. So we will find our x-intercepts by figuring out what makes the top equal 0. Y-intercept is the same for these as it is for all other functions. You just plug in x equals 0 and see what it gets you. And I'm not too worried about this. Here we go. We're going to graph this thing. And we're not going to write too large because it is a beefy question. Oop. These pens out of here. Pencils can go back in the jar. Okay. First, I don't like sideways fractions. I only did that to save vertical space. Okay. This this rational function has a higher degree in the numerator than it does in the denominator. This is what some teachers will call a top-heavy function. That means we don't have a horizontal asymptote. We have some other kind of in behavior asymptote. And because of that, we will have to use long division to find it. Okay, I already have a question back there. Yes, what's up? You have question face. You were making faces when I was saying that stuff. Bigger than the bottom degree, yes. It's third degree and second degree? Yes? Okay. All right. Anything that can be factored needs to be factored. And since this is AP, I am going to have to assume that you know how to factor the difference of two squares. X squared minus 9 instantly factors to x plus 3, x minus 3. There you go. Nothing is going to cancel out. Because no x's are canceling off the bottom, I know that this graph doesn't have any removable discontinuity, so no holes in this graph. But it does have two values for x that make me try to divide by 0. And since I have two values of x that would make me divide by 0, I have two vertical asymptotes. I have one at x equals negative 3, and I have another at x equals positive 3. We've already talked about the fact that it doesn't have a horizontal asymptote. It has an in behavior asymptote. We'll track that down using long division in just a moment. Before I do that, I want to go ahead and find my intercepts. An x-intercept implies that you are on the x-axis, and if you're on the x-axis, we know y equals 0. So what is the only way that my fraction could equal 0? That's the question we're asking ourselves. If the numerator is 0. So you could show the work of multiplying both sides by whatever's on the denominator, but it would just leave you with 0 equals x to the third. So clearly you have an x-intercept at x equals 0. I'm sorry? Oh, you could multiply both sides of the fraction, both sides of the equation by this denominator. But if you did that, it would just leave you 0 equals x to the third. Well, crud. Because the x-intercept is x equals 0, my graph goes through the origin, which means this is also my y-intercept. So I don't have a reason to plug in x equals 0, because if I plug in x equals 0 to find the y-intercept, I'm going to get 0 over -9, which is just 0. So this one, it has one coordinate that happens to be both its x-intercept and its y-intercept. That happens sometimes. Now it is time for us to talk about how to find an end behavior asymptote. We find end behavior asymptotes of top-heavy functions using long division. It's almost going to seem like a waste, but trust me when I tell you it's not. I need to make this x squared look like an x to the third. What am I going to multiply by? X. When I multiply this x over here, I'm going to get x cubed minus 9x squared. Okay, I'll tell you what, I'll throw a, minus 9x. I'll throw a 0x in here, just so like terms are lining up. Zero minus -9, that's plus 9. So I have a remainder, and that remainder is 9x. If you recall back some lessons ago, whenever we were first talking about long division, we said it's always going to be remainder going over divisor. So it would look like this. And this is where I started to lose second period. What does it mean to be an end behavior asymptote? It means asking how the graph behaves when x is remarkably large. Okay? And understand that we're saying our graph approaches this thing as x becomes remarkably scary, Trump ego size large. But if it had just been this, and we're allowing x to be gigantic, what's happening to this, Adi? Oh, crud, my phone is ringing. This is an opportune time. Anyway, wrong number. So anyway, this, think rational functions, go back to the other page where I put the star. This is bottom heavy. What does this go to as x gets really big? It goes to 0. Because this is bottom heavy, this goes to 0 as x goes to infinity. Which means my end behavior asymptote is the line y equals x. Because remember what it means to be an end behavior asymptote. What is the graph behaving like when x is really super duper big? To prove it to you, here's my calculator. I'm going to allow x to be a really big number. I'm going to let that number be 1 million. Okay? And I'm going to plug in 1 million to this whole thing. So we're asking ourselves, what will the y value be when the x value is 1 million? And the answer is so close to 1 million that the calculator can't show you how far apart it is from the actual answer. The actual answer is 1,000,000,00009. So as x gets bigger and bigger and bigger, the less and less and less this fraction matters because it's bottom heavy. When you do long division to find your in-behavior asymptotes, there will be a remainder. And when there is a remainder, that remainder will always be bottom heavy. Otherwise, you haven't finished dividing, which means the remainder portion of your in-behavior asymptote always goes to 0 and does not matter. Yes, Adi?
Will the in-behavior asymptote always be like the answer you get?
It'll always be the dividend, yes. So if I did long division and I got 3x minus 1, then 3x minus 1 is my in-behavior asymptote. If I do the long division and I get negative x squared plus 5x plus 2, then that quadratic is my in-behavior asymptote.
What do you need the fraction for?
The fraction was the remainder, and I was just showing you that that part will always go to 0. So it's always going to be the dividend without the remainder because the remainder will always head to 0. Always. And I want to show you on Desmos to prove it to you, but it won't show up in the video. So here's what we're going to do. We are now going to draw a small graph. Oh, no, we're not. Okay, yes? Yeah, that's what Adi just asked. Yes. The dividend will always be the in-behavior asymptote sans the remainder because the remainder will always go to 0.
Can it ever be simplified?
What do you mean simplified?
Like if you get a fraction and the fraction is simplified.
The fraction at the end is a remainder, and the remainder will always go to 0 because you're dividing by something with x's in it.
So the remainder will always go to 0, not
The remainder goes to 0. The dividend is the in-behavior asymptote minus the fraction at the end because the fraction at the end will always head to 0. She's looking at me like she doesn't understand what I'm saying. Let's say you did the long division and you found that this was your dividend. This part goes to 0. So this is your in-behavior asymptote. Because we're talking about what the graph acts like when x is really, really, really big. This will always act like 0 when x is really, really, really big. Because it'll always be bottom heavy. By definition, the remainder has to be bottom heavy. Otherwise, you haven't finished doing division. Does that make sense? Okay. Don't make this too large. Yeah, I'm just putting together my graph. These are my vertical asymptotes. Whose nose is squeaking? So the in-behavior asymptote is y equals x. That means whatever x is, y is, right? That means my asymptotes are going to intersect each other at 3, 3 and negative 3, negative 3. Because y equals x. Are you all comfortable with why I said this coordinate is 3, 3, and this coordinate is -3, -3? This is important to this question. Why is that? Because the line y equals x says no matter what x is, y will be the same number. So it would have been at 1, 1, 2, 2, 3, 3, 4, 4, so on and so forth. Yes?
So like if y is negative x, opposite.
Yeah, negative x has a slope of -1 like that.
Can it be y equals x squared?
Yeah, an NBA asymptote could be anything. It could even be this quadratic.
How would you just plug in the x?
I'm just graphing the line y equals x as a red dotted line. Yes?
Or if we got like 3x, would it be -9?
Yeah. It would have a slope of 3 if it was 3x. All right, because we haven't even started graphing yet. We know one coordinate of our graph. That coordinate is right here. We know it goes through 0, 0. Now there's going to be a lot of talking about stuff, very little actual stuff written down compared to what we're saying. So you're going to have to take notes on what is said based on whatever it is that you need to see. I don't know what your notes need to say, okay? Here's what's going on. If we were doing only a sign diagram, and I'm doing it way down here because I'm not actually going to use it, our vertical asymptotes will be like this, and we put dotted lines on them like that. And our 0 was right here at 0. Our sign diagram has been split into 4 zones. Can you see that? So our sign diagram has been split into 4 zones by the intercepts, there's only one of them, and the vertical asymptotes. Yes, Charlie? Sure, yes. Sorry. I just wanted you to see why I'm going to be addressing 4 zones. Okay? Because my x-axis has been chopped into 4 pieces. Great. The easy places to check are between the asymptotes. So I can grab a representative from here and a representative from here and plug them in and see what I get. If it's okay with you, I'm just going to use 1 and -1. 1 and -1. Is that okay? So let's figure out what f of 1 is. And I actually, to be real with you, don't care about the value. All I care about is the sign. I guess I will use the sign diagram, but I'm not going to. I'll do all my plugging in up here where I have space. Okay? It's a fraction. If I put a positive 1 right here, is this up here going to be positive or negative? Oh, whoops. Okay, well, I guess I'm testing positive 1 first. Positive. If I put a positive 1 right here, is this going to be positive or negative? Positive. And if I put a positive 1 right here, do I get positive or negative? Negative. The result for this, will it be positive or negative? It'll be a negative value. That means between 0 and 3, my graph has all negative y values. That means it's under the x-axis. Yes, Charlie? Oh, yeah. Always plug into the factor form. Makes your life easy. The only way that I can stay below the x-axis and get infinitely close to an asymptote, because that's what asymptotes are, things you're going to get infinitely close to, is if I do this. It doesn't have a choice. It has to be under the x-axis and get infinitely close to this vertical line. Now let me drop in x equals -1. Again, I don't care about the value. All I care about is the symbol. Negative 1 cubed, positive or negative? Negative 1 cubed is negative, folks. Okay. Negative 1 plus 3, positive or negative? And negative 1 minus 3, positive or negative? The result here is it positive or negative? Positive result. That means between negative 3 and 0, my graph is above the x-axis. But it has to get infinitely close to this vertical line. So it doesn't have a choice but to behave like that. Behave like a cubic in between my asymptotes. I am not surprised that I see a cubic looking graph between my asymptotes, because lots of experience and lots of practice have taught me some patterns. I don't want you to try to memorize these patterns. I want these patterns to come to you through repetition like they did for me. But the difference between the degrees, bless you, the difference between the degrees, is it an odd difference or an even difference? Odd difference. That's why this graph in between looks like a polynomial with odd degree. That's why its endings point different directions, because the difference between the degrees is an odd number. Yes? If it was even, like let's just say this was a 4, then there would have been a quadratic asymptote. If it was even as in a squared, then there would have been a horizontal asymptote. It's an asymptote that's shaped like a parabola. It's like this asymptote is shaped like a line. It'd be a parabolic asymptote. Don't worry, you'll see one in the notes. Alrighty. Now, the other two zones. The other two zones are where it's a little more challenging, and why I said it was important for you to understand that this point is negative 3, and this point is 3, 3. For the other two zones, I actually do care about the value. The value now matters. Okay? For the other two zones, I'm going to pick a candidate number from that zone. So I'm going to pick negative 4 and I'm going to pick positive 4. Let's see what happens at negative 4. Negative 4 to the third power is negative 64. Negative 4 plus 3 is negative 1. Negative 4 minus 3 is negative 7. I get negative, my apologies, 64 over 7. And I'm going to now drop in x equals positive 4. 4 cubed is 64. 4 plus 3 is 7. 4 minus 3 is 1. I get positive 64 over 7. Now, I don't know what 64 divided by 7 is. Here's what I need to know. Right here at this x value of negative 4, what is this y value? Negative 4 as well. This number, is it above y equals negative 4, or is it below y equals negative 4? It's below it. That is why the blue curve is underneath the slant asymptote here in this little triangular zone. And it has to get infinitely close to both lines. Once again, over here at x equals positive 4, what is the y value associated with that number? Positive 4. We now look at this y value. Is it bigger than 4 or less than 4? Bigger than 4, which means it's above this red dot. which forces my shape to look like this. That is a sketch of the graph. Adi,
Would it be like
when you say flipped, what do you mean?
instead of negative 64 being less than negative 4, it'd be bigger than?
If you had gotten a number bigger than negative 4, then we would have drawn a curve like that. And same thing would have happened over here. If I had gotten a number smaller than positive 4, then I would have drawn a curve like this.
Can you get like opposite numbers? Where, like,
What do you mean opposite numbers?
or can you have one in the corner like this and one like a long one like this?
Yes, this is possible, but not when the difference between the degrees is odd. Because let's talk about odd polynomials. Odd polynomials' endings always go different directions. Whereas even polynomials' endings go same directions. So they would have both been above or both been below. Okay? Yes, Charlie?
If the end behavior asymptote wasn't y equals x, would the
If-
2 on the outside still be the same but negative?
If it wasn't y equals x,
Yeah.
what would it be? What do you mean?
Like if like a different question, because of y equals 2x, would it still be like f of whatever the number is would be a negative and then
Well, if it's a 2x, if it was 2x, then this number at 4, you'd be dealing with a y value of 8. And this number is actually, is this bigger than 8 still? It's still bigger than 8, so it still would have been above.
so what I'm asking is they're still going to be the same number, but one's going to be negative and one's going to be positive.
No, that was just because this thing was symmetric around the y-axis.
Okay, that was what I was asking.
Yeah, well, not even symmetric, but because, let's say centered. Because this thing was centered at the y-axis, that was why we got the exact same number.
I was just wondering, like, if doing another question, if I don't get the same number, if I know it's wrong.
The number's not important. Where it is in relation to the asymptote is what's important. Okay? Out of curiosity, what time is this class ending today? 18. Okay, great. Enough time to do the next question. There was a question. Mark, what's up? Shh.
Do you only divide
Shh.
long division if the top is higher degree?
Top heavy, yeah. Top heavy is the only time you have to do this. Otherwise, you have a horizontal asymptote. Okay? Speaking of, this is not top heavy. This is actually bottom heavy. And if you look back to the boxed starred object yesterday, bottom heavy automatically uses y equals 0, which is the x-axis, as a horizontal asymptote. Before we do that, though, factor everything you can. There, fully factored. Because I have two different places that would make me divide by 0, I have two different vertical asymptotes again. One at x equals 3, one at x equals negative 2, Charlie. Since these are not the same number, this graph is not symmetric around the origin, to answer your previous question. Okay? It just so happened that this one was symmetric around the origin, whereas this one's not. Okay? All right. Hey, let's find our x-intercepts. X-intercept implies that the top equals 0, because that's the only way the whole fraction equals 0. So when does x minus 1 equal 0? Ah, yes, at x equals 1. My graph crosses the x-axis at positive 1. Does it cross the x-axis any other times? No, because that's the only way the top can equal 0. Y-intercept is a number I can actually find this time because it's not the same as the x-intercept. For the y-intercept, you literally let x equal 0, and you see what you get. And you get y equals 0 minus 1 over 0 minus 0 minus 6, which is positive 1/6. All right. So I have an x-intercept at 1, and I have a y-intercept at 1/6. I have my two vertical asymptotes. Oh, and it's bottom heavy, so I have a horizontal asymptote at the x-axis. We're ready to rock and roll. And I'll throw these little red dashed lines on the outside of my x-axis to show you that it's the horizontal asymptote as well. What do we have? We have a cross happening at x equals 1. And we have a y-intercept that is a positive number. This is just a sketch. So I hope you don't mind. I'm just going to do that. Now, we've already talked about the fact that there's only one way that the top could equal 0. That means there was only one x-intercept. That means as I go to the left, I can't come back down. Because if I tried to come back down, I'd hit the x-axis again. So the only way I can go from here to here and get infinitely close to this line is if it does this. Now here's what we don't know. We don't know after the number 1 if I bounce up or if I go through. Well, I know, but that's because I'm a nerd and I've done this a billion times. I know that because the difference in the degrees is an odd number, it's going to cross through this thing. But let's just say you didn't have that knowledge in your pocket. You could use sign diagram knowledge. You could ask yourself, what happens if I use x equals 2? If you say plug in 2 using sign diagram knowledge, 2 minus 1 is positive. 2 minus 3 is negative. Oops. 2 plus 2 is positive. This is going to result in a negative number. So that means at x equals 2, I'm down here somewhere, forcing the graph to look like a cubic. Are you comfortable with how that just happened? I used sign diagram knowledge. I already knew over here it had to go up because it went from here to here. Couldn't go back down because it can't hit the x-axis again. I just need to know bounce or cross. That's what I needed to know. And that's why I used the sign diagram knowledge. And I'm going to use sign diagram knowledge over here at x equals negative 3 and over here at x equals positive 4. Let's figure out what's going on at x equals negative 3. Again, I don't care about the actual number. All I care about is the symbol. Negative 3 minus 1 is negative. Negative 3 minus 3 is negative. And negative 3 plus 2 is negative. Resulting in 3 negatives gets me what? Negative. Under the x-axis. And the only way I can be under the x-axis and infinitely close to this line and this line is to get a shape like this. Lots of experience, lots of practice, and a deep understanding of how graphs work has told me that because the difference in degrees is odd, not only will these endings point opposite, I'll also use opposite ending boxes. So I know it's going to be up here. But until you are that good, just use sign diagram knowledge. So pick a candidate out there and plug it in. 4 minus 1 is positive. 4 minus 3 is positive. 4 plus 2 is positive, resulting in a positive number. I don't think it takes much work to double check that. And then do this. The directions were to analyze the graph though. So we still have to do that. All right, let's do some analysis. Where is this graph? We already know where its x-intercept and y-intercept is. We don't need to redo that. Where is it positive? It's positive from negative 2 up to the number x equals 1. and it's also positive after x equals 3. Now we're just looking at the picture. Where is it negative? The rest of its domain. Negative infinity to negative 2, and also 1 to 3. Here's a fun one. Where is it increasing? Nevers. It's never increasing. This is an always decreasing graph. So Mr. M, can I just say negative infinity to positive infinity? No, you may not. It doesn't exist at x equals negative 2 or x equals positive 3. And since it doesn't exist there, we don't use brackets. And the last thing we're supposed to do is limits as we approach our asymptotes. The left limit and right limit are going to be the same thing, 0. So I'm running out of vertical space, so I'm just going to try to squeeze it in here like this. The limit as x approaches negative infinity of f of x is equal to the limit as x approaches positive infinity of f of x is 0. By the way, giving you a little bit of heads up on this knowledge, the true definition of a horizontal asymptote is a limit as x approaches positive or negative infinity of f of x equals a number. When the limit to negative infinity or positive infinity equals a number, that's the true definition of what it means to be a horizontal asymptote. But now we need to approach our vertical asymptotes from both sides, and we can do that just by looking. The limit as x approaches negative 2 from the left, on the left of negative 2, down. The right of negative 2 is up. I could try, but then you can't see the picture anymore. See, it's going up as we get close to the right side of that line. I am so out of space. Goodness. If I'm at the left of x equals 3, downwards at the left of x equals negative 3. And on the right of x equals negative 3, it goes up, which you can see right there. So positive infinity. Man, get skinny, short, squat mathematics, right? Goodness. Sheesh.